somewhat tempted to include numerical analysis fundamentals and the Newton-Ralphson method. Okay, so this method says that the n plus 1 xn plus 1, this iteration is equal to x at n minus f of x at n by f prime of x at n. So we have to have a function and its value at some point, and then its first derivative and its value at that same point. Okay, so and the condition for this to be valid is that function at x naught should not be 0. Function at xn should not be 0. At this nth point, the value of function should not be 0. This is the condition for this theorem. So for example, the function we have is let's say 2x square, and the first derivative of the function is 2.2x is equal to 4x. Yes, and then the first iteration for the solution is equal to x naught minus f at x naught by f prime at x naught. Yes, so it goes so it cannot be 0, so we start with 1 minus 2x square, which is 2, and 4x, which is 4 in this case. So 1 minus 1 by 2 is equal to 1 by 2. Yes, and we go further. The second one would be x2 is equal to x1 minus f at x1 by f prime at x1. So 1 by 2 minus, so 2x square at 1 by 2 would be 1 by 2. We couldn't put 0. We started with 1, and now we have to put 1 by 2 here. So 2 into 1 by 4 would be 1 by 2. Yes, so in the numerator 1 by 2, and in the denominator 4 into 1 by 2, which gives us 2. Yes, 2 by 1. Okay, so let's write it more clearly. 1 by 2 by 2 by 1. Okay, so it gives us 1 by 4 in the second term, 1 by 2 minus 1 by 4, and now we have here, and 2 minus 1 by 8, which means 1 by 8. So we are now narrowing down. Sorry, once again. Oh, sorry, the LCM is not 8, but it's 4 here. Excuse me. 4 and 2 minus 1 by 4, which means 2 by 4, which 2 minus 1 by 4 is 1 by 4. Yes, so we're shrinking. So 1 by 2 or 1 by 2, 1 by 4, and now x3 would be x2 minus f at x 2 by f prime at x2. Yes, this would be 1 by 4. We start with this value 1 by 4 minus. Okay, now we put this 1 by 4 into x square. So 2 into 1 by 16 is equal to 1 by 8, and so this is 1 by 8 by, now f prime 4x would be 4 into 1 by 4, which is 1. It's 1 by 1. Okay, so we have this form. It says 1 by 4 minus 1 by 8, and now we have the LCM 8, and it says 2 minus 1 by 8, which becomes 1 by 8 in the end. So this iteration gives us 1 by 8. So we can estimate the numeric values as well, but from common sense we can see that the solutions or the error is shrinking from 1 by 2 to 1 by 4 to 1 by 8. So the more iterations we do, the further close we get to our final approximation. Yes. So for example, if somebody is interested in decimal values, so this is 0.5 and this goes out to be 0.25 and then 0.125 and then so on. Yes, so this depends on the number of iterations you do. So for the function you have, and with the condition that it shouldn't be 0, and following the steps, for example taking the first derivative and then starting with the first possible value which is non-zero. So we start with the numeric value 1 and then we go further, and that then starts giving you the iterations, the approximations. So let me write it more clearly. You see, so x naught, x1, x2, x3 and so on, 1.5, 0.25, 0.125 and so on. So this is actually as close as we can get to our solution when we try to define our interval. So basically what we're doing is we have a function on xy plane, and this function is behaving somewhat like this, and when it dips, you see this is the f of x, it dips here, and so this is the point of interest, and this intersection is our solution. The function dips on x-axis and this gives us the point of solution. Then we have to narrow down the bracket, the interval, as much as we can for the possible values. And in case this solution, this function is behaving somewhat like this, it dips and cuts the axis and rises and cuts again. So we have two solutions. Here there was only one solution, here we have two solutions, S1 and S2, and then we can do the further iterations, but that is a complex case. This is just a graphical representation. The first interval would lie around S1 and the second would lie around S2. Yes, the point of intersection of y at x. So you see this is x and this is f of x. This clearly shows what I mean. but we don't need to overthink. We just need to keep one thing in mind, that we have a function on xy plane, and it is a defined function, and it tips and cuts the axis, and here lies the solution within this interval, and we have to narrow down this interval as much as we can, and this is minimizing the error, or the fundamentals of numerical methods. So we are supposed to work on the quadratic equations. Okay, so quadratic equations, and there are many methods which can be used for solving quadratic equations. First is the quadratic formula. The second one is completing squares. The third one is factorization. And the fourth one can very well be substitution. Yes, so if we are supposed to solve it, we'll skip the first one, which is quadratic formula, and we'll work on the other methods, because formula we have discussed in a previous segment in the domain of complex numbers. So completing squares, two squares, and now we have this form. For example, x squared plus 2x is equal to -1. Okay, all right, it's just 0 for now. Okay, so what we do is we complete the squares. And how so? X squared plus 2x plus 1 minus 1 is equal to 0. So the square of the first term plus 2 into the first term into the second term plus the square of the second term minus 1 for mathematical quality gives us 0. Yes, so x plus 1 whole square minus 1 is equal to 0. So this becomes interesting, because the next iteration will give us x plus 1 whole square minus 1 whole square is equal to 0. Yes, square of 1 is 1, so we can do this mathematical manipulation. So what it does is x plus 1 plus 1, x plus times x plus 1 minus 1 is equal to 0. So x plus 2 into x is equal to 0. So now we have two solutions: x is equal to 0, or x plus 2 is equal to 0. Both are possible, and x plus 2 is equal to 0 implies x is equal to -2. Yes, so this is what we did with our squares. Now we look into factorization. Factorization, which is the, okay, let's do it this way now. Factorization, and if we have a form x square plus 4x plus 4, yes, is equal to 0. So it gets x whole square plus 2 into x into 2 plus 2 whole square is equal to 0. Okay, you see, so this is a formula in algebra. X square plus y square is equal to x square plus 2xy plus y square. Yes, you see, x plus y whole square is equal to x square plus y square plus 2xy. This comes from algebra, so this is what we are doing here. This gives us x plus 2 whole square is equal to 0, and x plus 2 is equal to 0, and x is equal to minus 2. Yes, this is rather using algebra. I'm making a small alteration here. I will tell you what factorization is. This is from algebraic relations. Okay, and now I will tell you what factorization is in the next step. Factorization in true sense of the word. So for the same equation, x squared plus 4x plus 4 is equal to 0, what we do is x squared plus 2x plus 2x plus 4, we split 4x into 2x plus 2x to have factors on both sides, common factors. So here we have x, so it gives us x plus 2, and here we have 2, gives us x plus 2. Yes, this is factorization. So x plus 2 times x plus 2 is equal to 0, and x plus 2 whole square is equal to 0, which means x plus 2 is equal to 0. This clearly means x is equal to minus 2, which is a seemingly valid solution. Now this method, which is substitution. Okay, so in this method we have higher degrees. For example, x 4 plus 4, x to the power 4 plus 4, x square plus 4 is equal to 0. So this is basically not a quadratic equation, but to make it a quadratic equation, we put x squared is equal to y, which gives us x4 is equal to y square. So we have a quadratic equation, but in terms of y, not x4. Okay, so y square plus 4y plus 4 is equal to 0. Now we solve this one, and it says y whole square plus 2 into y into 2 plus 2 whole square is equal to 0, which says y plus 2 whole square is equal to 0. Yes, That's the form. And y plus 2 is equal to 0, which means y is equal to minus 2. And y now, we know that it's equal to x squared. So x squared is equal to minus 2, and x is equal to minus 2 under the root. And x is equal to minus 1 into 2 under the root. And x is equal to iota under the root 2. So this is the solution with the substitution.